Hey folks, this video is, in case anyone wants it, to review for the AP Physics 1 exam, a unit-by-unit review of equations and concepts. I'm not going to go into super detail about any one concept, but this is more of a kind of guide to the big things that you want to review. So we're going to start, and I'll try and put a comment in there on YouTube pretty soon of the time where I start each unit. So if you wanted to skip to a particular one to hear it again, you can do that. So we start with kinematics. We kind of had two units of kinematics at the beginning, just linear motion and then projectile motion. So there's four equations for kinematics. Kind of before that we talked about position and displacement and distance. But once we got to acceleration, we had these four equations. So the two on the left and the one on the top right are on your equation sheet. The one at the bottom right is not on your equation sheet, I think because it doesn't have acceleration in it, but it is a constant acceleration equation. So you can use these equations for anything that is not simple harmonic motion, because in simple harmonic motion there's a non-constant force, and so there's a non-constant acceleration. And so in all other cases, there's a constant acceleration, at least in this course. A nice trick I want you to understand is that if you ever encounter something that is going at constant velocity, you can turn this equation into a constant velocity equation if you get rid of the 1/2 at squared. In other words, if acceleration is 0. It doesn't work with any of the other equations. If you wanted to do this one as a constant velocity acceleration, it would be v naught and v would have to be the same. So if the velocity was 3 meters per second, you'd plug in 3 for v naught and 3 for v. Really, like, the kinematics unit is all about graphs, knowing that the slope of a position graph is the velocity, the slope of a velocity graph is acceleration, the area under an acceleration graph is the change in velocity, and an area under a velocity graph is the displacement or change in position. So really it's all about, this course really hammers home velocity versus time graphs a lot, and so you need to know kind of everything there is to know about those types of graphs. Being able to tell the difference between constant velocity and constant acceleration and knowing how to deal with that, and then projectiles. So the big deal with projectiles, you have a parabolic trajectory because you have a constant horizontal velocity and a constantly changing vertical velocity. So acceleration is 0 in the horizontal direction because gravity only operates in the vertical direction. And then because of that, the velocity changes. It goes down by 9.81 meters per second every second. As far as the math goes, you probably won't be asked to solve like a typical projectile problem. You might, but you know, where does it land? You're not going to have to calculate a number, but you will have to know that the initial horizontal component of the velocity is v naught cosine theta, and the initial vertical component of the velocity is v naught sine theta. And so there's, a bunch of other things to investigate in the units, but the AP Physics 1 exam tends to stick to the broad strokes for kinematics. Forces is the first, really important unit in physics, and it's probably the most important. You can do a lot of physics with just the stuff that you learn in this unit. Obviously, we have Newton's second law. We have the force of gravity on an object. So expect there to be probably a question where you have to recognize that because objects have the same mass, they have the same force of gravity, or since objects have different masses, they have a different force of gravity. But remember, even though objects can have a different mass, generally speaking, if they're both falling, they will fall with the same acceleration. And that's because of Newton's second law. This force of gravity, this is universal gravitation, and this is the force of gravity between any two objects in space that are separated by a distance. This is the center-to-center distance. So if we were using like the sun and Earth, maybe the distance from the center of the sun to the center of the Earth. We have our friction equation, I'll talk about that in a minute, and then spring force is something that I introduced in this unit, and we looked at it in a couple other units. Second law is the most important equation in this course. It's really where every other equation comes from. And so you want to know everything there is to know about this equation. Being able to draw a free body diagram and calculate the net force, and use the free body diagram to build second law equations. Knowing that the net force and the acceleration always have to have the same direction, but neither of those things need to be in the direction an object is moving. If you have an object that's sliding but slowing down, then if it's moving to the right and slowing down, its acceleration is pushing to the left because the net force is to the left. We just talked about gravity on a planet versus in space, so knowing that there's two equations for gravity and knowing that little g is only good on or near a planet. Static versus kinetic friction, we have a less than or equal to sign. So if it's kinetic friction because the objects are sliding along one another, we use the friction force is equal to mu times the normal force. But if it's static friction, then we have to have more information to make a conclusion. So we say that the static friction force is less than or equal to mu times the normal force. So for static friction, mu times the normal force, it represents the maximum force of static friction, and static friction can be less than that. Basically, static friction will push back with exactly the same force you're using to push it until you overcome static friction. So definitely go back and review those concepts. Mu being the coefficient of friction, there's a different kinetic and static coefficient for every surface. Sometimes they're the same, but usually the static friction coefficient is greater. This kind of compares the amount of friction that's possible between surfaces, whereas the force of friction represents the actual force of friction. It does depend, the force of friction depends on mass of an object usually, but the coefficient of friction does not. Inclined planes and pulley systems, I'm not going to go into that here, but you should definitely know how to draw a free body diagram and analyze it for an object sliding down an inclined plane or sitting there at rest, as well as pulley systems. And I'll just skip the third law one. Knowing how to deal with a single object versus a system is incredibly important because you will be asked a lot of questions about internal versus external forces, and you'll have to analyze or derive equations for the net force on a single object versus on a system. And so knowing how to work with internal versus external forces is important. Finally, Newton's third law and force pairs. You will definitely be asked a couple of questions about Newton's third law specifically, but basically, forces come in pairs. So if you draw a free body diagram that has a specific type of force, let's say tension, then there has to be another object that is feeling the same force of tension in the opposite direction. And so that goes for every type of force, especially including gravity, that two objects exert a mutual force of gravity between them. Okay, so that's forces and kinematics. Next up is circular motion. This is one of the shortest units of the course. It's really just an extension of the forces unit. Once you have objects moving in a circle, the circular motion unit tackles things that are moving at constant velocity, or constant speed, sorry. And so the speed of an object in circular motion is 2 pi r over t. This equation is not given on your equation sheet because it's not an equation you can use all the time. There is non-uniform circular motion where objects are accelerating, and basically that was what our rotation unit was all about. So if we know an object's moving at constant speed, then the circumference divided by the time it takes is its speed. There is a centripetal acceleration for any object moving in a circle. It's a constant acceleration if the speed's constant, and it's a changing acceleration if there's an angular velocity or an angular acceleration. This is the only circular motion equation on your equation sheet. We also talked in this unit about orbital motion, and so we derived an equation for that. I think it's very useful to remember this equation because it's like not a pain to derive, but it can take you a little bit of time to remember how to do that. Okay, big takeaways for this unit. Any force is capable of causing a net centripetal force. So there's no such force as a centripetal force. It is the net force in the direction that is centripetal. Centripetal is toward the center of the circle. Whatever the centripetal direction is the positive direction. So if you have an object going around in a circle, the positive direction is in a different direction depending on where the object is relative to the center of the circle. So that's important. And really, like, I don't have this here, but rely on your use of Newton's second law for this one, because that's really what centripetal, what the circular motion unit is all about. In orbit, gravity, that would be Newton's universal gravitation, causes the net centripetal force, and this equation comes from that. Orbital speed is something that is constant for circular orbits, so like satellites generally have largely circular orbits. It depends on the mass of the planet, that's the big M, and the center-to-center distance between the center of the planet and the center of the satellite that's orbiting. So again, this is just an extension of Newton's second law and the forces unit. Next big unit in physics was energy. So there's lots of equations going on here. Definition of mechanical energy, the definition of work as a change in energy, translational kinetic energy, gravitational potential energy, elastic potential energy, power, and then this generic equation that I write that deals with the idea of work and also encompasses conservation of energy. So in the energy unit, it's very important that you understand whether a question is asking about an object or a system. If you're dealing with an object, then the only thing you can consider is the kinetic energy of the object. But if there's a system, that includes like the Earth or a spring, then there can be potential energy. And so knowing whether you're told to analyze an object or a system is very important. The big law in this unit was the law of conservation of mechanical energy, that this amount of mechanical energy is going to be constant as long as there's no work done by external net forces. Non-conservative work is what we focused on here. So let me backtrack a bit. So the sum of all the types of energies will remain constant as long as there's no work done by net external forces. And so for non-conservative work, we usually dealt with friction or any kind of mysterious force that just provided some change in the number of joules of energy. And so non-conservative work is generally pretty easy to spot because we're talking about we can analyze it from, was there friction or was there like a person's hand that caused something to happen? Those are kind of the obvious situations where there's non-conservative work. If you're ever in doubt, you can also work backwards. You will know that non-conservative work has been done if you can kind of prove to yourself that there's an energy change. And so like I do want to talk about this a little bit. One of the kind of big things that comes up every once in a while is if you're like holding something in your hand and then it's at rest and you slowly lower it down and place it on the table. That is a situation where non-conservative work has been done and the work done was negative because the object when you were holding it up was storing more potential energy with the Earth than when you got it to the tabletop. And since it never really changed its initial or final speed, there was no change in kinetic energy. So you decreased the gravitational potential energy and didn't allow that potential energy to become anything else. And so that's an example of non-conservative work. Kind of to piggyback on all this, work is not just FD cosine theta. So this is one way to prove that work has been done, but if you can also identify any change in mechanical energy, then work has also been done. A kind of side concept that we didn't deal with a ton is that work is equal to the area under a force versus displacement graph. So a force doesn't have to be constant, and we saw that with springs, and so if you find the area under this type of graph specifically, you can find the work done and the change in energy. Momentum is up next. That's kind of the last of the big three, and then the last two units are just a review of everything in different settings. So momentum, mass times velocity. I learned recently that momentum predated Newton's second law, and Newton's second law was written in terms of momentum. So this is a kind of more, you can maybe think of it as a more basic idea than net force. So mass times velocity is an important quantity in physics. And then this is the impulse momentum relationship. So a force exerted over a certain amount of time will cause a change in the linear momentum of an object. And so the big law in this unit was conservation of linear momentum, and it the linear momentum of a system is constant as long as there's no net external force. This is a little easier to spot than conservation of energy because usually the system that you're thinking about is easy to define. So it can be like two things of similar size that collide. And by similar, I mean like they could be two cars, but they could also be like a car and a bus. So they don't have to be exactly the same size. But if you're thinking about like a ball bouncing on the Earth, that's probably not a conservation of linear momentum situation because the Earth is so much larger than the ball. So in my head, that's how I kind of separate the big concepts. I'm going to use conservation, if I can, whenever the objects are similar in size, and I will think about impulse whenever it's obvious that the objects are very different size, right? A car and a wall, maybe. Impulse momentum is this equation, so you can kind of combine these two equations. Force times time equals mass times change in velocity. And also another side concept is the impulse is the area under a force versus time graph. So if you like flash back to work, we had a force versus distance graph, and this is a force versus time graph. So area under the graph does kind of follow along a bit. And you'll probably have some questions about area under force graphs. There are three major interactions we talked about for conservation of momentum: explosions, where objects push apart from one another; inelastic collisions, where things collide and stick; and then elastic collisions, where things collide and bounce. All three of them are conservation of momentum situations, but momentum and mechanical energy are constant specifically for elastic collisions only. So you can apply either conservation law if the collision is elastic. And then the last piece of this unit was when momentum is constant, the velocity of the center of mass is constant. So there are always questions about this on the exam, and they kind of take two flavors. One where they're kind of trying to psych you out, and the correct answer is that the velocity of the center of mass is constant, and one where they're presenting evidence where the velocity of center of mass isn't constant, and that is because there is an external force on the system. And so you want to watch out for evidence of net external forces on systems, because that also means that the center of mass velocity is changing. This can be counterintuitive because when objects collide, they obviously change velocity, but even in a collision, the center of mass will continue moving at the same velocity. And that's great. Simple harmonic motion is up next. This is where all the physics concepts that you've learned are put into a new setting. And so anything that comes before this unit is fair game within this unit. We will reintroduce the idea of period of oscillation. So circular motion and simple harmonic motion are very similar, and actually one is derived from the other. We have equations for the period of oscillation of a spring system and the period of oscillation for a pendulum system. All graphs are sinusoidal for simple harmonic motion when time is on the x-axis. When position's on the x-axis, the shape can change, but specifically all time-based graphs for simple harmonic motion are sinusoidal. Conservation of energy makes a big appearance in this unit because as a spring oscillates, there's a trade-off between kinetic and elastic potential energy, and sometimes gravitational. And when a pendulum is oscillating, there's again a trade-off between kinetic and gravitational potential energy. There can be objects interacting with the system, so when you take a pendulum and pull it back, that's not a conservation of energy system situation. Or if you take a spring that's hanging and you pull it downward, you are not making, like the mechanical energy is changing in that situation because you are adding energy to the system. And then the kind of last part of the unit was the period of oscillation of each thing. If it's a spring with a mass, then the only variables that affect the period of the spring are mass and spring constant. You want to be careful with this because there are, the mass can change, and in addition to changing the period of a spring, it can change other properties that have to do with energy. And then for pendulum, it's only the length of the pendulum and the value of little g. So you might be, there was a question we did, I think, in this unit about taking these two things to a different planet, and the spring would not change at all, but the pendulum would oscillate at a different rate in that simple harmonic motion. Last but not least is the gargantuan rotation unit, and so all sorts of equations. Again, this is kind of like the ultimate review unit. We enter into a new setting and learn a bunch of equations, but apply a lot of the same concepts. So we have 4 kinematics equations. They give you 2 on the equation sheet and kind of expect you to realize that like the other 2 are the same format as linear kinematics, but with all the Greek variables. So theta for displacement, omega for velocity, and alpha for acceleration. These equations are so rarely used in an exam, but really they are important. And I'll get back to them later. We have the idea of torque, of net torque equals moment of inertia times angular acceleration. So this is Newton's second law again. And then this idea of the moment of inertia of a system of individual masses. We are introduced to rotational kinetic energy, 2 different forms of angular momentum, and then the idea of angular impulse. So all major concepts that you've learned throughout this course still apply to rotating systems, but now there's like new variables and new ideas. The biggest way that these equations pop up is the second bullet point. Understanding the relationship between the angular velocity of an object versus the velocity of a point on that object somewhere. So if you have like 2 people riding a merry-go-round, if they're different distances from the axis of rotation, they would still have the same angular velocity, but they would have different linear velocities. Being able to draw a free body diagram for objects that rotate, knowing where to put the forces, so knowing that the force of gravity acts at the exact center of the object. The normal force comes from the ground and goes through the axis of rotation. Friction force, again, starts at the ground and acts parallel to the ground, and etc., etc. So you have to be able to put the forces where they act and in the right direction also. Being able to decide when torque equals 0. So that's like a big, that's a conceptual thing, and thinking like if the object's not moving, or if its rotation is at constant velocity, then net torque equals 0. But also knowing how a force could cause no torque. So think about like what we were just talking about with free body diagrams. The force of gravity cannot cause a torque on a symmetrical object because the value of r for that force is 0. It acts at the center of, at the axis of rotation. The normal force on a rolling object cannot exert a torque. It has an r that's equal to the radius of the object that's rolling. It has a force that's often equal to the force of gravity, but the angle is going to be 180 degrees because the value of r comes down from the center, and then the force pushes straight back toward the center. So all of this to say, forces that point directly through the axis of rotation create no torque on the object. For I equals the sum of mr squared, you want to only use that if the mass is distributed in a way where there's 1 or 2 or more locations where the mass is. If the mass is evenly distributed, you cannot use this equation. But if all of the mass is concentrated in specific locations, then you can use this equation. And it happens every once in a while. Something that was just elucidated by the most recent free response questions is with rolling objects in an inclined plane. And it's the idea of work. Static friction is the force that acts to cause objects to roll without slipping. This actually represents conservative work in a way. So there's no like displacement associated with the force of static friction, but there's rotation associated with it. So static friction for objects rolling down an incline, that work that's done by friction and that torque is used to generate rotational kinetic energy. So friction will take, friction will cause there to be less translational energy for things rolling down, but for an object like a block sliding and a cylinder rolling, they do different things. For the block, kinetic friction does non-conservative work to dissipate energy. For a cylinder, it's going to do conservative work to generate rotational kinetic energy. Last topic was angular momentum, and so there's, we talked about different styles of angular momentum conservation. Maybe like the figure skater one, where there's a spinning person or object, and they're changing their own moment of inertia. And we talked about there being like an inverse relationship between those two things. If the person pulls their arms in, their moment of inertia goes down, but their angular velocity increases. And so their angular momentum is constant, even though they're changing. Rotational collisions, if we have a rotating object and another rotating object like hits it, then we have that sort of collision. And then this is probably the least common of the things that you would see, just because it doesn't happen as much in everyday life. But linear and rotational collisions are very common. And so we have this equation of L equals I omega, but also L equals RP. So I omega is for objects that are rotating and can rotate. RP is for objects that are moving in a straight line that enter into the rotational system of something else. And so this linear rotational collision, you would typically have an object that is capable of rotating and an object that's moving in a straight line, and they would collide with one another. And so that is another very common situation in momentum. And that is an overview of everything. I hope you enjoyed it, and I hope you will ask questions. Thanks.